Hello again, everybody. We're back for another exciting physics lecture. So, here we go. Today we're going to talk about things that are on ramps. So, basically, what we've got is a situation where we've got some kind of ramp and we've got something on it that's going to slide or roll or not quite fall down the ramp but go down the ramp. So we might have a block that's going to slide down. We might have a car that's going to go down the ramp. We could have a skier going down the ramp. Sometimes our ramp is going to have no friction. Sometimes it will. Once in a while, we're going to have things going up the ramp as well. And what we'll do in that case is we might have like a pulley up here and some big old weight tied to our block like that, and it's going to go up the ramp. Or anyway, we're going to do a whole lot with ramps. So we're going to introduce them now. We'll be coming back and forth to them quite a bit. So anyway, that's what we're doing. Let's talk about something first. What's going to make something go down a ramp? So let's pretend for now that our ramp has no friction. So it's made out of ice, or it's super smooth in some way, or maybe we have a car with really good wheels and it's going to roll down the ramp. Okay, so what's going to make the whatever move is going to be gravity. Gravity is going to be pushing straight down on it, but a little bit of gravity is going to push whatever we have to go down the ramp. All right. Now I want to try something. We're gonna do two kind of silly cases. Over here, we're gonna make the angle of our ramp, that theta, we're gonna make it get smaller and smaller and smaller. So I'm going to have theta go towards 0 degrees. So imagine with me what's going to happen. All right, eventually I'm going to have the ground. I'm not going to have a ramp at all. All right, so now my little box that's sitting on my ramp is not going to move at all. We're going to have the acceleration equal to 0. It's not going to accelerate. It's just going to sit there. It's not going to move to the left or the right. Now here's our other silly case. Here we're going to have theta go towards 90 degrees. So it's going to get bigger and bigger and bigger until basically what we have is a cliff. There's my theta. It's 90 degrees. So again, this is going to be a little silly. Like I said, we put our box on our cliff. Well, what's our acceleration going to be? Basically, we just dropped it off the cliff. So now our acceleration is going to be the acceleration because of gravity, and it's going to accelerate at 9.81 meters per second meters per second squared. So you guys, these are our two cases. So the biggest our acceleration is going to be 9.81, and the smallest it's going to be is 0. When we have a ramp, any theta in between there is going to give us an acceleration in between 0 and 9.81. All right, not too hard, but I just wanted you to see that. The biggest we're going to get for acceleration is 9.81. The smallest is going to be 0. All righty, let's move on. So a little bit of bad news, but good news is coming. Now, I took our ramp that we had at first, and I put a box on it, and then I put an X and a Y axes there. Okay? Now, here's the bad news. let's have a look at what direction this thing is going to move. Which way is it going to speed up? It's going to speed up going down the ramp. So guess what? My acceleration is going to be that direction, right? It's going to be less than 9.81. It's going to be bigger than 0. But here's the biggest problem that we're having. That's at some goofy angle to the x-axis. So if we start doing math with this, we're going to have sines and cosines and everywhere. All right? What about our velocity? Well, our velocity is going to be in that direction too. Okay? What about our displacement? When later on, if our box is down here, well, our displacement vector would have some funny angle as well. So all of these things are at some cattywampus angle to our axes, which is going to mean the math is just nasty bad. Okay? So, guess what? Here's the good news. We're not going to do that. We're still going to do math, but we have a solution. So check this out. Let's tip our axes. Fantastic. So now, guess what? A is only in the x direction. Our velocity is in the x direction. Sorry, got to make those vectors. And our displacement, when our box ends up down here, guess what? Our displacement only goes in the x direction. Woohoo! That's fantastic! Everything is in relation to x now, is in relation to going down the ramp. That's great news. The only thing we have to do angles with is gravity now, because gravity is trying to push this box straight down. Can you see that? So we have our acceleration due to gravity, okay, is in this direction. Now it's not gonna, our box is not gonna move that way, but that's the way gravity is trying to make the box accelerate. So guess what? We only have one vector we need to fuss with. Okay? So that's why we're going to tip the axes. Now, we're going to do a big, bad, nasty drawing next. Okay? And what I want you to do is copy this drawing down very, very carefully. I'm sorry. I keep jumping back and forth here. Okay, so first of all, draw what's in black. Draw our ramp. Now, be careful. Do not draw theta at about 45 degrees. Make theta smaller than 45. Make sure you can tell the difference between theta and the other angle that's on the other side, this upper corner here. Okay, make sure that angle and the angle with theta on it, this one, are different sizes. So look in my drawing. I made theta little, and the other one's definitely bigger. Then I want you to put the axes on, x and y, and the box, and put the acceleration from gravity on. That's the way gravity is trying to pull this thing down to the ground. Okay? When you're done, go ahead and start me up again, and we'll go from there. Alrighty. So here's what we're going to do. Part of gravity is going to push this box down the slope. We know it's going to move down the slope, so something must be trying to move it down. And something is going to be moving it, trying to push it down into the slope, to hold it onto the slope. Let me show you what I mean. So let me draw these two vectors before you draw anything. So just watch for a second. Part of this gravity vector is going along the ramp, and that's going to be A of gravity in the x direction. Can you see that well enough? A with a little g and an x after it. Part of the acceleration due to gravity is going to be trying to get the the block to go down into the ramp. So it's going to be this way. And that's going to be the acceleration from gravity in the y direction. All right. Now I'm going to move the y vector over. So I'm going to slide it over so its tail is connected with the gravity in the x direction. Okay, didn't come out exactly right. But I want you to look at that triangle right there. Okay, I made a triangle right there. Have a look at it. Now, it's got a right angle, it's got a little angle, and it's got a big angle. All right, let's put those on there. Have a look. We have a right angle, which is right there, and check it out. The little angle is over here. That is theta, and the big angle's up on the side. Okay? So now, kind of tip your head sideways to the left, and let's do our trigonometry on this. Okay? This is going to be a little tricky, so hang on with me, okay? Let me slide this down a little bit, make the page longer. There we go. I want to know what A of gravity in the x direction is. A of gravity in the x direction is going to equal, now have a look, that's the opposite side from my theta. Okay? Now, let's go back up here. In blue, I'm going to remember my sine and cosine. So I have sine of theta equals opposite over hypotenuse. Okay? So then I can solve for the opposite side. It equals h times the sine of theta. That's the one we're going to use here. So we're going to use that right over here. Now look, my opposite side is A of gravity in the x direction. What's my hypotenuse? Well, my hypotenuse is little g. All right? Oh, sorry about that. I had to stop for just a second. Let me get my thoughts back together. We're finding A of gravity in the x direction, and it's going to be g, which is the hypotenuse, times the sine of our angle. All right? Now, that's a big one. If you want to remember that, that might help. So this will be true whenever our angle theta is measured from the ground, from the flat. Okay? Now, the other side, the part that's going to push down into our little ramp here, which isn't going to be important right now, but in a little while it'll become that way. It's going to be A of gravity in the y direction is going to equal the hypotenuse, g, times the cosine, sorry about that, c, cosine of theta. Okay? Not as important. The big one for us is going to be this g times the sine of theta. That's going to be our new acceleration. Okay? Now, real quick, our sine of theta goes from 0 to 1. Okay, so if we multiply g times 0, our acceleration will be 0. If we multiply g times 1, our acceleration is going to be just g. All right? So those correspond to an angle of 0 or an angle of 90. All right? A flat or a cliff, like we talked about earlier. We're going to be playing a lot with this in our problems, so don't stress if you're a little bit lost. Just hang in there, and let's move on. Here is your video problem. All righty. Enjoy yourselves. Thanks a lot. Bye-bye.